Hello again, and welcome to another review session for your final exam in Calculus 3208, presented as always by CDLI. And we're somewhere around the middle of our unit on anti-differentiation and integration now. And we're looking at limits and Riemann sums today and putting the two of those things together and to give us one grand idea here. So let's see where we can get with all of that. Start with the three things we're going to focus on. So we're going to use limits to find exact areas under curves. So we're going to take our Riemann sums and let's see what we can do with limits to make that stuff exact. So I guess the analogy to that from our differential calculus that we did is when we used the limit difference quotient to get the exact slope of a tangent line from our estimates. We're going to do something similar to try and get the exact area under a curve. Then we're going to look at a few special formulas that we have, or formulae I guess is the correct plural, for looking at sums of some special sums and some of the formulas that we can use. And then we'll use just a couple of those. We don't spend a lot of time on this topic. It's more about understanding, but we're going to use just a couple of those to evaluate the limits of some basic Riemann sums using the limits. So I guess the analogy of that would be actually, remember we used to actually calculate derivatives using the definition of the derivative with the limit and difference quotient, etc. Well, this is, the analogy for this one is the same kind of thing here. So taking the limit of a Riemann sum to find the area under a curve is really the same type of procedure. It's very much the long way around, and more so than it was with the definition of the derivative. It's a tricky way to get at it, especially if there's anything complicated at all with the formulas. So we just do a couple of simple ones, and then we'll jump into seeing how we evaluate those areas a little more concisely. Okay. So now that I've spieled on, let's get started. Okay. So let's think about the general idea of what's happening here. So we're going to try to improve our estimates that we had for areas. So we're going back to our old friend y equals x squared. That's the graph we have here. So all of these curves are y equals x squared. Okay? And so the first graph that we have on both the top and the bottom, so we're going to move left to right across this. So the first graph that we have for both of these is we're trying to find the limit, or sorry, not a limit, we're just trying to find an estimate for the area under the curve using Riemann sums. So over here you can tell by the fact that all of the top right corners of all of our rectangles are touching the curve that we're using right sums up here as indicated by R, and over here we're using left sums because the top left corners of our rectangles are touching the curve. Okay, so that's what happens if we use 10 rectangles. So notice the estimates. Up here that says 0.385 and this one says 0.285. Okay? So now what we're going to do is we're going to try and improve our estimate by increasing the number of rectangles. Now there's good and bad about that, but overall it does improve our estimate. So let's see what happens. You'll notice that when I increase the number of rectangles from 10 to 30, so these two graphs here, we're using 30 rectangles to estimate the area. You're getting more little areas that are going to help the overestimate. There's just more of them. But at the same time, they get so much smaller that the actual area that you're overestimating by here is much less than it was in the first case. So all these little bits that are above the curve now, because they're getting so small, we're actually losing out on less and less, or counting extra. So down here we're missing out on some of the area because we're below the curve, but up here we're counting extra. And we've gone from an upper estimate that was at 0.385 to a new upper estimate at 0.3502. So obviously that's better. If it's still an upper estimate, but it's lower, it's got to be better. And our lower estimates have gone from 0.285 to 0.3169, so that's also an improvement. So basically what we can say at each stage of the game here, we're changing our upper and lower bounds. We started at the first case here saying 0.285 is less than or equal to our area, which we knew had to be less than or equal to 0.385. And now, after going to 30 rectangles, we can see that 0.35, whoops, forgot the 302 is less than or equal to our area, which we know has to be less than or equal to 0.3, whoop, I got them backwards, don't I? Yeah. 0.3169, sorry about that, is less than or equal to our area, which is less than or equal to 0.3502. So we've narrowed it down. We're only off by about 4/100ths there. And then in the last case, what we do is we find out that our area has now been wedged down between these two guys. So what happens is if we continue to take left and right hand sums, we're going to get better and better and better and better estimates. Okay? and it sort of squeezes the area in between them until we figure out exactly what that area is going to be. Now, how could we figure out exactly what the area is? Well, we got up as far as 50 rectangles in our third step here. 100 rectangles would be better, but it wouldn't be perfect. 1,000 rectangles would be really, really good, but it wouldn't be perfect. It would probably be more than we could get with 5 or 10 decimal places. The error would be that small, but it's still going to be an error. How big do we have to get? How many rectangles would we need? Well, to be perfect, we'd have to have an infinite number of rectangles. So let's take a look at where this is heading. What we're going to do is we're going to talk about exact area by using the limit of a Riemann sum. And the way that we're going to talk about that limit is we're going to say we want the limit. So remember, our left estimate was below area, and our right estimate was above. Now that's not a truth that holds for everything. That only works if we have an increasing f of x. Okay, so f of x has to be an increasing function for this to hold, but that's okay. So for the example we had anyway. But what we're going to do is, instead of saying that the left-hand limit is always below, or the left-hand sum is always below and the right-hand sum is always above, if we take the limit as the number of rectangles we're using approaches infinity, then those two limits squeeze together and end up at exactly the same thing. So their limits are actually the same. They're actually right at a. So the exact area under the curve of f of x, so any function f of x as long as it's continuous, the exact area under the curve on the interval from a to b can be found using either one. It doesn't matter if they both get to the same place. So we can take the limit as n approaches infinity of a left-hand sum, or we can take the limit as n approaches infinity of a right-hand sum. Okay, so we do that, and there's a couple of notes that we're going to talk about here. For this left-hand sum, remember that I'm talking I0 up to n minus 1. That means x0 is, of course, the very leftmost x value we can have on the whole interval a to b. And of course the xn that we would have over here for the last point, which we don't include in the first one but we have in the last one, is the value of b, which is the farthest we can get to the right on the entire interval. And so delta x that we're referring to, and we've seen this before, but delta x is b minus a over n, so the entire width of the interval divided by the number of rectangles. Sometimes you'll actually see these limits written not just as, sorry, I'll just get rid of this so I have a little more space, and this one too. Not just as the limit as n approaches infinity, but some textbooks actually you'll see them write limit as n approaches infinity and delta x approaches 0, which it's kind of redundant to say that, because if n is approaching infinity, then obviously look, delta x is going to approach 0, but sometimes they say that anyway. As long as we define delta x, that should be unnecessary, but that's the idea. So we're getting more and more rectangles, and the width of each one is shrinking really, really small. Okay, let's jump along and see what's coming next. Now we're going to look at, this seems way off track. We're not even talking about rectangles here, but we are still talking about sums, and you'll see we'll put all this together in an example in short order there. So these are some special sum formulae. And they're just 3 that, I mean, most people don't have them memorized. They don't keep them in their pocket every time they're waiting for a bus to haul them out and look at them. But mathematicians would know what these are, and they could tell you. So the sum of the first n integers, our old friend Gauss did this when he was very young, but the sum of the first n integers, or as we call it, sigma I equals 1 up to n of I, is always n times n plus 1 over 2. So in other words, if I wanted to add up 1 plus 2 plus 12, well, I've got 12 numbers, so it's 12 times 12 plus 1 divided by 2. So that would just be 6 times 13. So that's 78. So it's a shortcut formula for finding the sum of the first 12 integers, or the first n integers in general. These next two are similar, and their formulae are a little more complicated, but what they are is, instead of just finding the sum of the first n integers, this first one here gives us the sum of the first n perfect squares. So let's say if I wanted to find the sum of the first 4 perfect squares, remember what that means? I'd be adding up 1, and 2 squared is 4, and 3 squared is 9, and 4 squared is 16, etc. Okay? So those are the perfect squares, and the next one is just the sum of the first n perfect cubes. So if I add up the first, so 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, they get bigger faster, 4 cubed is 64, etc. So if I want to add up the first n of those, either one of these formula for however many n I'm using would tell me exactly what the sum of those is. What does any of this have to do with the price efficient over? Well, let me tell you. We're going to use these formulas to help us figure out in short order how to find some Riemann sums if we take their limits. You knew it was coming. Here we go. So it says determine the exact area under the curve of f of x equals x squared on the interval from 0 to 1 using the limit of a right sum. This is the only example I'm going to do in this session. And I know we're looking at examples to help us review for the exam, but if we're going to get this to help us with the next thing, it's more about a concept at this point. So let's have a look. The limit of a right sum. So let's write out a right-hand Riemann sum. So Rn is going to be equal to the sum from I equals 1 up to n of f of xi, so whatever the x value is at a given endpoint for an interval, times delta x. Okay, so what we have to do is try and break all this stuff down so we can get all this nonsense inside here in terms of n, so that if I want to find out the exact value of what's happening here, I can get the exact area as being the limit as n approaches infinity, and I have everything I need in terms of n in one tidy package. Okay, so this is what I'm after. So let's see what we can do. First of all, let's look at delta x. We should remember delta x is defined as the width of the interval b minus a divided by the number of subintervals n. And we're going to let that number of subintervals get really big, but in this case, it's b minus a will be 1 minus 0 over n. So it's 1 over n. Okay? So delta x, I'm going to, in a second, replace that with 1 over n. The other thing I'm interested in looking at is, I know I can use, instead of f of x, evaluated at xi, I could take xi squared. But what in the heck is xi anyway? Well, let's see if we can figure that out. So xi, well, let's think about this. We're going on the subinterval from 0 up to 1. So x0 is the leftmost point, or it's a, right? So a equals x0, so that's going to be 0 here. Then, to get to the end, the right end of my first interval, I'd have to add the width of the interval, which is my delta x. So x1 here is going to be equal to 1 over n. Then to get to the endpoint, the next endpoint on the subinterval, x2 would be adding another one of those, so it would be 2 over n. And then, etc., x3 would be equal to 3 over n, dot, 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 yada, yada, yada. And xi basically is I divided by n. Now that's a little bit abstract, but that's what we need for this. So xi is going to be equal to I divided by n. All right, so we have to take all of this information and somehow put it into that formula to help us calculate the exact area under this magic curve. Okay, let's hope that we can get it to work. I'm just going to hide this over here for a sec so I have a little more space. Okay. So now I got to rearrange this formula or make it a little bit nicer. So I want to take the limit of that. So I want the limit as n approaches infinity of the sum from I equals 1 up to n of f of xi. Now f of x is x squared, and xi we just saw was I over n, and we have to multiply by delta x, and delta x in this case is 1 over n. Okay, so that's lots of stuff happening there. Whew. So let's see what we can do. We're going to take this limit as n approaches infinity. Now, I'm going to simplify what's inside there a little bit. I'm going to say we're going from I equals 1 up to n of I squared times 1 here will just be I squared, and then it's over n squared times n, so that's n cubed. Now, as the value of I changes from 1 up to n, the value of n down here is not affected, but the value of I up here is. So I can pop this n cubed out of the sum. But I can't take it out of the limit because the value of n is dependent on what's happening as n approaches infinity. So we've got two competing operators here. We've got this limit and that sum guy. So we've got the limit as n approaches infinity. I can take the 1 over n cubed out of there, but I can't take it out of the limit. So I've got this now. So it's I equals 1 up to n of I squared. Okay. Now how in the heck am I going to evaluate the sum from I equals 1 up to n of I squared? Hold the phone. I'm going to jump back one slide for a second. That's the sum of the first n perfect squares. We saw that already. So we can use this formula. It's n times n plus 1 times n 2n plus 1, all divided by 6. So I can replace that entire sum with just this. Oh, that's nice. So I'm going to come back over here, and what I'm going to have is the limit as n approaches infinity of 1 over n cubed times, so all of this now, we said we can replace with a formula that tells us the sum of the first n perfect squares, and it's n times n plus 1 times 2n plus 1, all divided by 6. Okay, so there's lots of stuff. So all I have to do now is evaluate this limit in terms of n. Well, if I multiply everything on the top together, I'm going to get a polynomial expression. And in the denominator, 6 times n cubed is already a polynomial expression. So what I have here is the limit of one polynomial over another, which is a limit of a rational expression. It takes us all the way back to the second unit of the course, limits. So let's do this. I'll multiply these two binomials first and then multiply them all by n after. So this is going to be n outside of. We're going to have 2n squared plus 3n when I add those like terms together plus 1. So I did that quickly and added my two middle terms together. And then in one more step, I've got the limit as n approaches infinity of 2n cubed plus 3n squared plus n, all divided by 6n cubed. I don't know about you, but I'm tired. Okay, let's keep going. So we've got the limit as n approaches infinity of all of this stuff. Now let's take a look. Remember, how do I evaluate the limit as n approaches infinity of a rational expression? Well, there's lots of different ways. Multiply by the reciprocal, the highest power of n, and all that, but we had some shortcuts. And what we said was we look at the highest power of n, so the degree of the numerator and the degree of the denominator. And they're the same. And if the degrees of the numerator and the denominator are the same, then what we do to evaluate the limit is we know it's just going to be the ratio of the leading coefficients, which in this case is going to be 2 divided by 6. So that limit is 2/6, or just 1/3. What does all of that mean? What does it all mean anyway? It means that if I looked at a graph of y equals x squared, and I looked at the interval that goes from 0 up to 1, the interval that we've been talking about, right there. So that part of the parabola, it means the exact area underneath here. This exact area is 1/3 of a unit in size. Well, let's think about that. All the way up to here, this point has coordinates of 1, 1. So this whole square is 1 by 1. So that's got a unit, an area of 1, that whole square. We've got less than half of it. So I'm willing to believe that. Alrighty. Here's the your turn question. It's the same question, except you've got to do the thing for evaluating the area under the curve f of x equals x cubed instead of x squared. All right, so good luck with that. Try to follow through the formulas that we had. This is not something that you want to practice forever and ever because it's not the most important thing to be able to do in calculus, but it's a good way to get the idea of the underpinnings of things, okay? So here's the solution, and it's all worked out in its gory detail, and this time we get a quarter. Is there something funny going on here? I think so. All right, so we got a quarter for the solution. Let's highlight some key ideas, and then we'll jump ship. So the key ideas here are not much to it. Remember, these were our formulas for Riemann sums, and if we want the exact value of the area, we just take the limit as n approaches infinity for both of those. And for some special functions, these areas can be computed using the sum formulae that we had. So the limits of sums are often cumbersome and difficult to compute. As we just saw, we will develop a much more concise and convenient method in the next section for finding exact areas. Hope that was helpful. If you have any questions, post them up. Good luck studying.